I would like to walk through an example with you of how you can solve a truss using the method of joints. We'll look at this truss here. I drew this truss in CAD, and as the note says on the bottom of the slide, here's the name of the CAD drawing, Structures21 truss example. So here's my Structures21 truss example. I maybe did more steps than you want to do, I don't know. One thing I will point out is when I solved the reactions using our equilibrium equations, I went ahead and using the mText editor, I inserted the sigma symbol in here, sum of. If you want to, you can just go steal this formula and blop it into your drawing, if that's easier for you than inserting your own symbol. In model space here, here's me doing all the steps, doing a free body diagram, tip to tail, blah, blah, blah. So let's look at this example. And remember our steps in the method of joints. We're going to go through these steps one step at a time. We'll work through them methodically. This is your cookbook. And here is the truss that we just looked at in CAD, which you are welcome to. Go get yourself a copy. And this is what we know about this truss. Some sizes, and there's an 11,000 pound load. Maybe hanging down from it, maybe that's an 11,000 pound truck driving across. So step one, we're going to draw a free body diagram of the truss as a whole. Here in the bottom corner is the original truss with all its bars inside. For the truss as a whole, we can ignore those bars inside. We're just going to draw a trapezoid-shaped beam. That's all. And it's got reactions, and it's got the 11,000 pounds. Why did I put an X and Y reaction arrow at A? What is A? A is a pinned connection, so it has an X and Y. What is F? F is a roller connection, so it has only Y. And now, step two, I'm going to solve those reactions. Well, let me back up here. Looking at this free body diagram of the truss as a whole, how many forces in the X direction do you see? Only one. You only see this reaction at A in the X direction, and if all the forces in the X direction add up to 0, that one must be 0. So from now on, we can ignore the X reaction at A. Now, I'll rummage around in my toolbox, I'll get my equilibrium equation, and I will use sum of all moments equals 0 to find the reaction at F. And so here I worked through it, force times distance, and I found that F was 7333. Then I went on to sum of all forces in the Y direction equals 0, and I used that to find how big is the reaction at A. All right, so now I know what numbers to write on my free body diagram. I'm going to write 7333 for F and 3667 for A. I'm starting to make my force summation diagram already. So now I've got forces in there. I can use those. Because now I'm going to go on to step 3. Find a joint with no more than 2 unknowns. Well, I could start at A and I could start at F. I'm starting at A for no particular reason. So I will make a free body diagram of the joint at A. And think about what direction these things are going. You know that a truss is just a funny shaped beam, and that means that that bottom chord has to be in tension. It's getting stretched. That bottom bar is in tension. And if you picture this thing getting bent, here's the reaction pushing up and another force pulling down. It looks like that bar AB is going to get squished, doesn't it? So it is probably in compression. It's pointing toward. So there's my free body diagram at joint A. Now, in CAD, I will take those three arrows and I will put them tip to tail. The only one whose length I know is this 3667, so I can draw that to length. AC, the horizontal force, I don't know how long it is, so I'll just draw a big old long arrow. AB, the sloping force, I don't know how long it is, but I'll just draw a big old long sloping arrow at the right angle. And I'll make sure that these arrows are all going tip to tail, around in a circle. When I get that, I can then measure the length where these arrows intersect, and I find out that the slopey one measured 4584, and I found out that the horizontal one measured 2750, as it happened. So now I am going to write those numbers on my truss. This is the beginning of my force summation diagram, and when you're done with your truss, every one of these bars will have a number on it, and you'll just go around adding them one at a time. So I started at A with a free body diagram at A. I did a tip to tail. I found out how long these forces were, and now I'm adding them on my diagram. And I write T for tension and C for compression, because it's important to keep track of which direction those forces are going. All right, now I'll move on to another joint with no more than two unknowns. What's my candidate? Well, F over here looks like a candidate, so I'll make a free body diagram of that. There's my free body diagram. And now I will draw forces tip to tail from joint F. The only length I knew was this reaction, 7333, that we solved earlier. So I can draw that one the right length. EF, I don't know how long it is, so I'll just make a big old long arrow. And the slopey one, I don't know how long it is either. I did assume it must be compressing. It must be pointing towards. So there's that one. And now I can measure how long those lines are. And here are the numbers I came up with. 9166 and 5500. And now I can write those numbers on my force summation diagram. And let me back up. And notice EF was in tension, DF was in compression. So when I write those numbers on there, for EF I write 5500 T for tension, and for the slopey one, 9166 C for compression. All right, next step, move on to another joint with no more than two unknowns. This is probably the only candidate I've got, so I'll pick this one. It's got 1, 2, 3 forces. I know one of them, I don't know the others. So there's my free body diagram. Now, in this one, I don't really know what direction to put this vertical arrow. I do know that because this is a truss, which is just a funny shaped beam, I know that the bar at the top of the truss is going to get squeezed. It's going to be in compression. So I know I can draw arrow BD pointing towards the joint because it's compressing. And I already figured out that this slopey bar, AB, is getting squeezed, so it's in compression. It's pointing towards. Well, look at those arrows. If this joint is in equilibrium, and all the forces have to add up to 0. You've got a slopey bar pointing up. That means you've got to have some y direction stuff pointing down. Otherwise it would fly apart. It wouldn't be in equilibrium. So from that, I concluded this vertical one must be pointing down, which means it's pulling away its intention. So that's how I drew it. Then I made them tip to tail. I found the numbers, and I put those numbers on my force summation diagram. Now I'll move on to another joint with no more than 2 unknowns. Oh, this one is good because it's a nice square thing. I could draw a tip to tail, but I don't have to because all the forces in the x direction add up to 0 and in the y direction add up to 0. So that was quick. Now, the only other unknown bar, I'm looking at my force summation diagram here, the only other unknown is this slopey bar here, CD. And I could draw a free body diagram down here at the bottom or up here at the top. Kind of doesn't matter which one. I just picked the one at the bottom for no particular reason. There's my free body diagram. And again, I don't know whether this slopey one is in tension or compression, but I know that I've got one bar in tension for sure, because I figured it out before. It's pulling away, it's pointing up, so this bar has got to be pushing down for it to be in equilibrium. Some of it up, some of it down. So that's what direction I drew that arrow. And now I can arrange those arrows tip to tail and measure the unknown one. And now I can add that final force, 4584 compression, C for compression, to my force summation diagram. I am done. That is my final truss. So here are all the forces on the bars, and when you go to my CAD drawing, you can see all my free body diagrams and all my tip to tails. And that is what you need to do in your drawing. You need to draw all these steps just like I did in my CAD drawing. So first, free body diagram of the truss as a whole. Figure out how big the reactions are. Then pick one joint with no more than 2 unknowns. Could be A or B. Draw a free body diagram at that joint. Draw a tip to tail, and put both of those on your CAD drawing, just like I did. Free body diagram and a tip to tail. When you get the numbers, add them to your force summation diagram, then move on to another joint, so on and so forth. I point out here that this particular truss has 5 zero force members. And you can probably spot 1 or 2 of them already without straining too hard. You probably can spot 2 joints with only 3 bars in them, 2 of them in a straight line. That means the third one is 0. So you're going to find out that a lot of these bars are 0, and you have fewer bars to analyze than you thought. So there you are. Help yourself to that CAD drawing, which is your cookbook.